Hello everyone, today let us understand how to solve such a square resistor problem and find the resistance of this. As you can observe, all the resistances are equal in every path. So we can approach this with a different method. Normally, if the resistances were unequal, we will require to make this circuit planar. And we will be using a lot of star to delta conversions to get the resistance of the circuit. This is the case when the resistances are not equal. But here, as they are equal, we'll be using another method, which will require. What basically happens in this Ohm's law multimeter method is, suppose if you have a network and you connect a voltage source to it and we give it a current. Based on the resistance of this network, the current flows through it. Here R will become V by I. In such a way we can find the resistance of this network. This is what we are going to apply to this circuit. So these are the target terminals A and B. We have to find RAB. To solve this complex circuit, I am going to inject a voltage across it. So I'm going to connect a voltage source across this circuit. You have to choose the target terminals. The B is over here. You will have to choose the path through this way. So you have to basically figure out what the target terminals are. Now we'll be solving this problem considering that this and this are the target terminals. A and B are the opposite sides of this diagonal cube. We can observe that this circuit is in symmetry. For a circuit to be symmetry, all of the resistors should be equal, but that reason alone is not enough. So along with this, the path resistance must also be equal. We can see that all of them are 1, so it makes all the path resistance to be equal, and therefore we can call this a symmetrical circuit. We know that when the voltage starts flowing through a resistor, it creates a voltage drop and the voltage reduces. At this level, the voltage is at its highest, but as it goes through these resistors, it drops down to a certain value. So at this point, the voltages are same. So we can consider it as a second floor, and this is the third floor where the voltage is at its highest. And here all the voltages are same. And when it comes to this point, the voltage is further reduced to a lower value. And let us consider this to be the first floors. And this is the ground floor where the voltage is at its least. The conclusion of having this circuit to be a symmetric is that we can apply current division rule. This is how we are going to solve this circuit. You can apply KVL in any path and solve this circuit. But we have to apply the current division rule first. Assume that the current flowing through this is I, and when it reaches here, it divides into 3 equal paths. As the path resistance is equal, the current would be I by 3, I by 3 and I by 3. So I is being divided into 3 equal parts. But when it reaches here, it is further being divided into two parts, so it gives out I by 6 and I by 6. Similarly, do it for the entire circuit. As soon as you reach the first floor, you will need to be adding these I by 6, and this will be adding up to I by 3, and this is going to be I by 3, and this is I by 3. And when you add 3 I by 3s, you will get it as I. So we can see that the incoming current is equal to the outgoing current. Now let me apply KVL in this path. You can apply it in any path and you'll get the same answer. In this loop, the current through this would be I by 3 and the resistor is 1 ohms. So the voltage first, this would be minus V, and then current I by 3 into 1 ohm resistor, and then I by 6 into 1 ohm resistor, 1 by 3 into 1 ohm resistor, this will be giving out 0. So by solving this, you'll get I into 5 by 6. We know that RAB is V by I. So we'll get RAB as 5 by 6 ohms. This is the answer.